Well, good morning. I want to start by thanking the committee for having us here to talk about this important topic of structure constructability. Since my webcam is on, if I start to get pit stains, please somebody pops a note in the chat for me so I can make sure to mention at the end of my presentation. But all kidding aside, this is a very important topic on structure constructability. And besides training the technicians, inspectors, resident engineer staff, I would say that this is Cameron and my probably most important duty as our job, and something that we talk about and think about all the time. Constructability affects all of us at this conference, whether we're planners, designers in construction, or even in maintenance. It all touches us in some way, in some form or fashion. It's anything, we always say anything can look good on paper. We can draw it, it looks good on that 2D plan set. And if a roadway designer designs all these real pretty spirals and curves and complex geometry and changing supers, and we draw it up, and the structure gets designed, well, it looks good, but does that mean that we can actually build it that way? Well, maybe we can, but at what cost? Is it additional costs? Is it additional time? Or maybe there's limitations in our equipment, our screeds, different things that can cause problems because of that. Maybe we end up with thin rebar cover, or cracking in our concrete that we did not anticipate or obviously don't want. So those are some of the things that we have to think about, and we want the designers thinking about that. A designer that has never spent any time in the field is at a disadvantage. So it's our job to make sure that we're sharing these lessons to the designers and the planners, so that we think about these things at the upfront stages and not wait till it gets in the field when there's a problem. Historically, we've always done the design, bid, build process. And so it is up to, the resident engineers and construction unit staff to share these lessons learned. Over the years, the last several years, with the introduction of design build into North Carolina, it's really opened up an opportunity for designers to work hand in hand with contractors and to kind of change that mindset and really be thinking about that constructability from the onset. How does crane availability or crane size affect how I design this bridge? Access, different things. What's the most economical way to build this? And so those lessons learned that the designers take away from that process can be applied to all their projects. I've seen, and Cameron will agree as well, even on design build projects, some of the topics that we're going to cover today can get overlooked by designers and contractors even. So we just want to share some topics that we've seen over the last several years that kind of continue to be a problem. We may answer some questions of, why do we ask for certain information from the designers when we're thinking about constructability before a project starts as well. So with that, I'm gonna turn it over to Cameron, and he's going to begin with a topic that he's very passionate about and one of his favorite topics. So I'll turn it over to Cameron, and we'll kind of share topics as we go through this presentation. So thanks again.
Good morning, everybody. I'm trying to advance slides here. Okay, here we go. As Aaron said, we've got one of the things that we focus on in the, Aaron and myself especially, is when we start looking at constructability, there are some deck geometry factors that really factor into how easy the project's going to be to build. And we've got factors like skew, the crowns and super elevations, vertical curves and horizontal curves. All these factor into how easy is it going to be to build that deck. And by themselves, none of these are a really big deal. The problem comes when we start combining these. And the design manual will tell you that when you've got two or more of these conditions, that's a concern for us, and we probably need to have some conversation about it. Skews outside the 75 to 105 degree window, that means that we're going to have to finish the deck on a skew if it's outside that window. That combined with a vertical curve or transitioning super elevations or crowns, all these things play against each other when we start trying to set that screed up and get a good riding deck. Crown transitions also pose problems for us. So that's the first thing we want to start with here is kind of explaining why these things are a concern to us and what they do. The first one we'll hit here is the skew plus a crown, and this goes back a long way. Skew plus crown equals bad. What happens in this situation, and I'll have some videos here in a minute that will demonstrate this a little better, but the screed bogey, and I'll explain if you don't know what that is in a minute, what that is. It wobbles across the crown point, rounds off the crown. It's very hard to get a good dry run when you got this situation. And on one side of the deck, we're going to have a lot of trouble with the cover or at the headers when we start trying to cast this deck. And as Aaron said, there's a lot of things that we can do, but a lot of times it adds cost. We can correct this situation with an extra piece of equipment from the manufacturer and an extra piece of screed truss. But again, that's another cost that we're building in that people will try to avoid if at all possible. Now, real quickly, when I'm talking about the bogey, this whole thing right here is the bogey. Here's your screed truss. These are the carriage rails up here that hold the bogey up, and this whole thing here is your bogey. So just to clarify that. Now, one of the problems we end up with, that last slide, if I can back up to that. In a normal situation where you're on a 90-degree skew, which we always want to cast a deck on a 90-degree skew, everything's fine. The truss and the bogey are square to each other. But the problem comes when we start, we get on that skew. And you can see this is a pretty severe skew on a project that I was on. This joint in the truss right here actually lines up at 90 degrees with this joint. But when you look down that, deck, you see that it's lining up with a completely different joint over here. This joint lines up with that one. So where do you set the skew? I mean, the crown into that truss? That's one of the problems we start looking at. And I want to show a quick video here. This one is one that comes from our Bidwell Corporation. This is showing what's going on. This is the normal situation. We always want to see a 90-degree skew, and that's the easiest thing we can finish with. But when we get into a skew with a crown, these are the problems that we start running into. You can see that these wheels that are supporting the screed are, first of all, you got parts that are clashing into the side forms. So we have to put the bogey on a skew. And we want those drums always being parallel to center line. But one of the other problems was those wheels were crossing this crown point at a different time. And what that does is it makes that screed wobble as it crosses. So this is the extra piece of equipment I was talking about that a contractor would have to buy to compensate for that. And again, that's more expenses, more trouble that ends up coming into the equation when a contractor starts bidding these jobs. All this little piece of equipment does basically is move those wheels to where they cross that crown point at the same time. This blue section is also a special length piece of truss because you want a joint on this side and a joint on this side lining up with that crown point. And that's another expense that comes in to play with this. All right, the next video that we've got here sorry, I'm having a little trouble figuring. Okay, this one's homemade. I apologize for the quality of this, but what this is showing is I made this little mock-up of a screed truss, and this is looking at one where we're set up on a 90. And what I want you to notice is as this little makeshift bogey I made, the pencil represents the drums on the roller. And if you're on a 90-degree skew, you can see that as it crosses that crown point, on both sides of the crown point, those drums are parallel with the surface that you're finishing. And that's what we always want to see. But made another little mock-up here, and it is showing that if we turn this thing on a skew and we don't make any more adjustments to it, we don't move where those wheels are crossing that crown point, it's going to show what happens. You can see on this side, sorry about that. All right, once again, you can see that if we don't make compensation for where those wheels are hitting, we're on this side of the crown, we've got those drums parallel to the surface that we're finishing. But watch what happens when it crosses that crown point. The front end, and this is due to the scale of this, it's very exaggerated, but the front end of those drums tips down. And I've seen a lot of problems come out of that. That will be, we have a lot of trouble, as I said, with the dry run on this half of the deck. We've had places where we just eat headers up when we've got into them. And that's where this kit that we have to buy comes into play. And if you see on this example here, on the next one, what I've done here is I've basically shifted this thing to where it represents moving those wheels to where they cross the crown point at the same time. And as it progresses, you can see on this side of the deck, we're parallel with the deck. And when you cross that crown point, those drums remain in contact. Remain parallel to the deck. So hopefully this is just an explanation that is telling you why it is that we don't like these things. And I feel like, the more I understand about something and other people's concerns, the better job I can do myself. And I'm hoping it's the same way with you guys. I don't want to just tell you we don't like that. I want to tell you what the problems are that we encounter when we get into some of these designs and geometries. And one of the big things that I want everybody to take away from this is me and Aaron and all the area engineers, we're here to talk to any of you guys. And we very much would encourage you, if you have any questions about any of this on a specific project, please call us. I had I don't know if he's on the line or not, but I had a project just a month or two ago, and Mark Cheek called me about it. And we were looking at it, and there was a simple solution to the problem we had. He had this exact situation on the bridge, a crown and a skew, and we got to looking at it, and it was early in the process, and noticed that, well, there was a slight curve coming in on each side of the bridge. The correction that we could easily make on that one is we kept the super elevation all the way across the deck, eliminated the crown, and it took this whole factor out of the equation for us when we get to the construction of that project. All right, skew and a vertical curve. It is not physically possible to set up a screed to finish the exact correct deck surface if you have a skew and a vertical curve combined. What we end up having to do is pick a happy medium. And to kind of explain that a little bit, I've got this next slide here. This is our representation of a deck. And here is our center line going across that deck. Now, when you're on a skew, you'll notice that all these points across this header are at different points along that vertical curve. So if you start taking each one of these points and you sketch those up, what you end up with is this. That vertical curve is showing up in that header. So as I said, we can kind of pick a happy medium to go across that thing. That's not too big of a deal. But one of the things that we end up with is this right here is what your screed's going to be finishing. That carriage rail is going to be set up straight. So we end up actually, this is a case of a crest vertical curve that is showing up in that header. We're finishing this, so we're actually losing cover at each one of these points. The screed is going to be shaving off a little bit more than it's supposed to be. Now, where this is going, this is the reason that we have started asking in this situation for the designers to supply us with header elevations so we can have a look at this. This distance may not be consequential. There are several factors that play into this. How steep is that curve? How wide is that deck? And all those things play together to tell how much cover are we losing. And of course, cover is the best protection we ever have for corrosion in that deck steel. So these distances right here are what we're really interested in. Are we losing 1/8 of an inch and it's no big deal right here, or are we losing 3/4 of an inch of that cover and we're starting to get concerned about that? Now if that's just the situation we've got and we're stuck with it, we can compensate for that. Even we can artificially introduce a crown into that truss. And even though it is, that deck's supposed to be on a straight grade, what that does is, you saw in that last picture, there was a pretty significant cut right here at the middle of this bridge. And if it was, like I said, if it was 1 inch of cover we were losing, well, maybe we put a crown in this, and that basically just splits up that vertical curve into 2 smaller vertical curves. And, the point of it, there are ways we can compensate, but we really need to have that conversation with you guys if we get into these situations. This is the information that we're asking for. And you can see right here, we have the grade elevation along that header. And we have figured what that screed, we basically put a straight grade elevation line in there too. And we're figuring the difference between them. In this situation, the worst case down here, we're losing about 1/8 of an inch. Not a big deal. And we can live with that. If Aaron or I looked at this and we saw that there was 3/4 of an inch in this column right here, if we were losing 3/4 of an inch of cover, we would be concerned about that. And we would want to be talking to the designers to say, okay, what can we do about this? And, can we increase the cover to compensate for it? Can we put some notes in the plans about putting that artificial crown in there to minimize the effects of this? But again, it's the conversation that we need to have between the people at each end, the people that are doing the structure design and the people closest to the construction of it. We need those conversations to happen. And just for your information, 1/2 inch is basically what we start worrying about. When we lose more than 1/2 inch of cover, that is the point at which we think there's a lot of concern about having to do something to compensate for that. Okay. Next subject we've got, and as I said before, that parabolic curve, we can't exactly match that all the way across that deck. We can pick a happy medium, and it's still not going to be perfect, but we can make it work. The next situation is transitioning crowns and super elevations. You can do a lot with these machines, and we can go from a super elevated cross section on one end of the deck to a crown on the other end of the deck. But that's another thing, like Aaron said, you start having to have specialized equipment and other pieces that the contractor may have to buy from the manufacturer, and it just complicates things. And if there are things that we can do to eliminate these, then that helps. I wanted, this is where that adjustment has to be made. And if the contractor doesn't have the right equipment, he's got to have a guy out there walking around in the concrete, cranking on a crank in order to do that, or he has to buy special equipment. So we like to eliminate things like that as much as we can. Next slide here. This is a bridge that we did that, an example of when we had, well, pictures aren't showing up. We had that situation. We had a transitioning super elevation. This bridge went from a normal crown on one end to a super elevation on the other end. And you can see in the rail here on one side of the bridge, this shows up. And you can see this is a median barrier. You don't see any kind of a bend in it. And this is the other side of the deck, which is going in the opposite direction. Now, this one, we worked it out because we took the effect of that crown section out of it. This had to be phased. So each side of this bridge was pretty much its own super elevated section. We didn't have to deal with that crown. So again, the whole thing I wanted to get out of this, problem geometries can be mitigated for in many situations, but please, we're always available. Give us a call. We would be glad to talk to you about any concerns or anything that might pop up on a design that you have any questions. Is it constructible? That's what we're here for. And we're going to turn it back over to Aaron now, and he's going to talk about pour sequences.
Well, thank you, Cameron. I believe they're going to transfer control to me here in a second, but pour sequences, this kind of goes along with the topic that Cameron was just talking about on how we're setting up our screed and the impacts that has, that the design has on how we do that. So if you're a structure designer, you're probably very familiar with this, this little diagram here. This is basically indicating the Wisconsin pour sequence, which in essence basically says that we want to pour our bridges in such an order that the deflection comes out of each span before you pour over these each interior bent. Because whenever you pour the spans on either side of the bent, it deflects and it creates a negative moment over top of the bents. And so if you've poured the concrete over top of a bent and it's already been poured, it's set up, or if it's starting to set up, get an initial set, and then you start getting deflection out and you create that negative moment, it puts the top of the deck in tension, which can lead to cracking. So we certainly want to avoid that. So that's first and foremost very important. We have to follow it. It's in the design manual for structures. And so for the most part, our designers design the pour sequences in accordance with this chart. Occasionally we have plan errors and we try to recognize those and correct them. But the next step is something that most designers are probably not aware of, and it could impact how you set these pour directions. If we start changing the pour directions, we have to start moving header locations, but I want designers to understand what the implications of these next topics are. Hopefully I can get the slides to advance here. Okay, so what I'm seeing here is what is a finishing pass? So Cameron talked about some of the components of the screed, and this is an indication of the two drums. As you can see here, they are both spinning clockwise, and you can see the little the bead of grout in front of those rollers. So as the carriage travels from right to left on the screen and the drums spin clockwise, they're pushing that grout to the left side of your screen. So that's what's called a finishing pass. And for those that have been on a deck pour or have seen it, as the carriage comes back the other direction, at least when we're on a skew, the drums don't change direction. They continue to spin clockwise, which we call a consolidating pass. So it's not pushing grout. And as it goes back and forth, you have a finishing pass, a consolidating pass. So that's that kind of important to understand what a finishing pass is. So next slide. Let's see here. There we go. So when finishing on a skew, there's some rules that we have to follow, and these are listed in order of importance. And so I'll be talking about each one of these and why we need to do this. But the first one is to finish from leading edge to the trailing edge. Second one is finish up the super elevation, and then the last one is finish downhill. Now that last one may surprise some of you because you've probably always been told to finish uphill. But that's that things kind of changed a little bit, so we'll talk about that at the end. So next slide. All right, so this is kind of a diagram of the screed set up on a skew, and you can see how the screed, the carriage, and the bogie is set up with the drums parallel to the direction of pour. Here we go, see if I got control. Okay, here we go. So you can see now what the leading edge is up here on the top right of your screen. The trailing edge is down on the bottom. And the direction of pour, we're going from left to right on our screen. So that's kind of defining what the leading edge and trailing edge is. So rule number one, that was finishing from leading edge of the machine to trailing edge. Why is this so important? So the way I always like to think about this is I kind of in my mind think about those drums as a squeegee. And if I line that squeegee up parallel to that deck and I take that squeegee and I slide it from that leading edge to the trailing edge, as I go down that from that along that truss, that water, or in our case, grout, where is it going to be coming out? It's going to be coming out the front of that squeegee or these rollers. Well, why is that important? Because as I move my whole screed forward, that grout, I'm going to be finishing it again and again and again, and I keep pushing it forward. Whereas if I do my finishing pass from the trailing end to the leading end, and think of it as a squeegee, as I slide that thing along that truss, all that water, or in our case, grout, is going to be coming out the back of those drums. And as I move forward, what I'm doing is I'm leaving a ridge of grout with every pass. And if you've ever been out on a bridge and you see a grout ridge every 6 inches or so, there's a good chance that they possibly finished it in the wrong direction. So that's rule number one. I've got a real short video here that will show you kind of what the finishing pass looks like. So just doing a finishing pass coming back the other way, the grout is kind of coming out the front of the drums. Okay. So that was kind of loud on my end. I don't know if you could hear me talking, but as that finishing pass, as it came back, finishing from leading edge to trailing edge, the concrete or the grout was coming out of the front of the roller. So that's what we want. We don't want to leave it along the backside. So it's very important. All right. So we've got rule number one behind us. Let's talk about rule number two. So rule number two says that we want to finish from the low side of the super to the high side of the super. We want to be pushing that grout up to the high side of the super. So as we're pouring from left to right on this screen as the direction of pour, and we have to finish from leading edge to trailing edge, we also want to be finishing up the super elevation. So this is where it's really going to impact the pour direction, because if our low side is on the right, then we're going to be doing that backwards, and we're going to be breaking rule number two. So again, the low side is up near the lead edge of the screed. The high side is on the trailing end. And when we finish, we're finishing from the low side to the high side, which is what we want. So whenever we're looking at this pour sequence and considering the Wisconsin pour sequence, one more thing that we need a designer to think about is those rule number one and rule number two. How is my pour direction with those two rules going to be impacted by this? So if I've drawn it up like this and I think everything's good, but that's going to have me finishing from the high end of the super to the low end of the super, I might need to make adjustments and go back to the drawing board on my pour sequences. So we're going to go through just a quick example. This is a bridge. It's on a 06 super from right to left. And you can see on the bottom, I've kind of labeled indent 1, indent 2, my low side of my super and my high side of my super. So if you kind of have your orientation, how the bridge is laid out here. So our planned pour sequence is to pour from indent 1 to indent 2. So let's go through the process and see if this is correct, if this is going to violate the rules. So if we're pouring per the pour sequence, we're going to finish. We got to do the first pour from leading edge to trailing edge, right? So that's rule number one. So as we finish from leading edge to trailing edge, we can do that in that pour direction. All right, but what does that do for our finishing to the high side of the super? In this case, because we had to do from leading edge to trailing edge, which was our most important rule, with this pour direction, it made us violate rule number 2. So that's no good because it's making us finish to the low side of the super. We're going to be pushing all that grout down the super and it can lead to problems. So what do? Let's try the other direction. So if we change the pour direction to pour from indent 2 to indent 1, So now when we screed from leading edge to trailing edge, we've obeyed rule number 1. So remember our low side and our high side. So now, because we finished from the low side to the high side, we've also met rule number 2. So this pour sequence should be going from end bent 2 to end bent 1 to be able to obey rules number 1 and rule number 2. So again, as a designer, you need to be thinking about these things. How do my pour, if I'm on a skew, how is a contractor going to have to pour this thing? And these are the things to think about. You know, if you're on a, you know, 02 super, it's probably not that big of a deal. But if you start getting 03 and 04 and higher, pushing that grout down the low side is going to create problems. So that leads us to the last rule, which was finishing downhill. Again, that probably caught some of you off guard because even our design manual says to pour uphill. And that a lot of times is what a lot of designers go off of. And you look at pour sequences and they're designing it to pour uphill. That has changed, and it's going to be changed in the design manual because that is not as big of a deal as it used to be. And so you know, Bidwell actually recommends pouring downhill. So it can go either way. We need to obey the other rules before we start changing our pour sequence to go uphill or downhill. And again, that's the least important of the 3 rules. All right, I'm going to pass it back over to Cameron and let him talk about detour bridge offsets.
Aaron, there's a couple of questions in the chat. I've answered one of them. There's a couple more you might want to hit while I'm going through this.
Let's go ahead and, okay, we'll go ahead and I'll answer them verbally at the end if we have time.
Yeah, we'll go through it. I just thought you might want to type or something while I'm jabbering. Okay, detour bridge offsets. How much room is enough room between the detour alignment and the old bridge and especially the new bridge in order for us to build a deck? Let's see if I can advance. Okay, I'm having a little trouble advancing here, guys. All right, thank you. This is a bridge that is in my area. You can see here's the old bridge. This is the temporary bridge. And have we got enough room there? Is this enough in order for us to build the project? Next. All right, one of the problems that we ended up with on this specific project is there was nowhere that told us actually what is that distance right there? What's the distance between the old alignment and the new alignment? And especially if Aaron or I or one of the area engineers are looking at preliminary information like hydraulic surveys or PGDs, this would be some very handy information to have. But it's hard to tell from the information that we normally get. And in this situation, we had the survey party had to run the alignments to be able to tell us how much we had. And in this particular situation, we had 6 feet between the proposed new alignment and what was shown for the temporary detour. As Aaron said before, I believe you discussed something about we don't really know what kind of bridge the contractor is going to use. We put a temporary alignment on there. We tell the contractor what that minimum span is that we want, and we leave the rest to him. We've had contractors use the standard supplied temporary trusses from maybe Sunbelt or Acro. We have had contractors build their own. We've had them use cord slabs. We don't tell them what to do, but we need to kind of make sure that whatever they use, we're going to have enough room to use here. In this situation, we had 6 feet. Now, normally 6 feet sounds like it might be a good number, but is it? Let's go back and look. This is a standard truss from one of these temporary bridges. And in looking at the plans for this project that we had, this was the width that the designer was counting on. He was specifying a clear roadway width. Well, there's a whole lot of stuff sticking out here beyond that clear roadway width that is going to take up room on this bridge. And how much is that? The 6 feet that we were talking about was shown from right here over to the edge of the new superstructure. This particular one is from maybe or now they're Sunbelt, but it is showing some of the dimensions, and you can get this information's freely available out there. But if you look on this particular one right here, 27 feet is this A dimension. So how much room do we actually have? If we start breaking that down, half of that 27 feet right there, that's 13.5 feet from the center line, which we had that, the center line of our detour alignment. We've got this extra 2 foot 4 3/4 inches right here. And that gives us 15, 10 3/4. Now let's take 12-foot lane off of that so we can figure out what we've got sticking out right here. 3 foot 10 3/4. So pretty much we've got 4 extra feet sticking out beyond where that clear roadway width was of bridge that we've got to do something with. There it is, 4 feet. Now that's just out to this center chord. So probably got another foot besides that. So on the temporary bridge side of the equation, where the two spans may be clashing with each other, we're looking at a minimum of 5 feet beyond where that clear roadway distance is. And it gets worse. Now, if we go back out to the end of the bridge, we're looking at there's an additional 3 feet of wings sticking out beyond the edge of that superstructure. And on the particular project I had these pictures on, we ended up having to we had moved some piles around and phase construct this end bent because the substructure for the temporary bridge and the substructure for the new bridge were clashing. So is 6 feet enough? Well, we just saw that we had 5 feet from that clear roadway distance over to the extreme part of where our truss is sticking out, or the substructure for our truss is sticking out. We've got an extra 3 feet of wing sticking out here. So we're trying to fit 8 feet of something into a 6 foot space. No, we didn't have enough room on the 6 feet. All right, so let's complicate this a little bit more. What about shoring? All right, we've got, let's say 10 feet. All right, we've got 10 feet. We're gonna assume 10 feet now, and we're gonna give the contractor 10 feet from the edge of the new superstructure over to the clear roadway distance. What's this gonna look like? All right, if we've got a substructure for this truss sticking out maybe this far, we've got a substructure for the new bridge sticking out 3 feet beyond that edge of superstructure. And we're going to have some room. If the end bents are in conflict, we're going to have some room probably for some temporary shoring. Now this setup right here, 10 feet would give us that. We've got that 3 feet. We've got the 5 feet on this side, and that'll give us 2 to 3 feet in the middle to put some shoring in for our substructure. And Aaron, you jump in, you discuss these quite a bit if you want to, but the things that will be helpful to us when we're evaluating some of this stuff, especially early in the process, is what distance do we actually have in relationship to those two alignments, or to the edge of the superstructure and this alignment? Then we can, if we know that distance, then we can work with that and kind of make a call as to whether we need a little more room or not. And I know with right-of-way limitations and stuff, we're trying to keep those detour structures as close to the new alignment as we can, but we need to have room to build it. Did you want to say anything on this slide, Aaron?
I was just going to say that, a lot of times on the roadway plans, we'll get this view that shows the existing and the detour alignment and the structure shown, so we can kind of at least visualize it, even though we don't necessarily have the offsets. A lot of times on the permanent plans, all we get is the alignment without the bridge shown, so it's really difficult to see, what kind of room you're talking about. So here lately, I've been getting a lot of emails from consultants and structures management with basically a cross-section view showing, kind of some of those earlier slides that really details what that offset's going to be, what's it going to look like. So I think that's important to continue to do. And in this little animation where the detour bridge got longer, it just kind of indicates, where is that end bent going to line up in relation to the other end bent of the existing or the proposed, because that could make it worse or better as far as our conflict. So just something to be thinking about, and make sure you provide the information to us to be able to review in an appropriate way where we can evaluate it.
Okay, so back to our original question: is this enough room? When you're just standing there looking at the temporary bridge and the existing bridge, everything looks fine and dandy, but this is what we ended up with. We had some serious concerns on this one as to whether we were going to have to phase, have a longitudinal construction joint in there and phase this thing or not, because these jacks that hold up your overhang, they only come in certain dimensions, and that, these are the standard jacks that everybody's got. They make a smaller one, but again, that's special equipment that the contractor might have had to rent or buy in order to narrow this up. And you can see we also ended up having a little bit of trouble with the MSA wall. But again, that's one of the things we ask you, please pay attention to, is how much room that we've got, because that clear roadway width has got some more that gets tacked onto the side of it. We've got truss, we've got something out there beyond that, even if it's nothing but some substructure that is holding up that temporary structure. So just please bear that in mind. And this is back over to Aaron, if somebody will give him control on the
yeah. So again, Cameron mentioned that Sunbelt has purchased maybe, so I've got it listed as maybe, but it's Acro maybe sizes. So the reason I put this slide up here, I just wanted you to be aware of the standard sizes that that maybe and Acro have on hand. They do have some customized, but it's a limited inventory. And not that we have to design our clear roadways to match a particular supplier. Because like Cameron said, we have some contractors build their own, but a good portion of ours are supplied by these two companies. And so knowing what the standard sizes are will help us to, first of all, save costs, because if we specify a clear roadway slightly or in between two sizes, they're either going to have to fabricate a new one or potentially widen out the bridge, which could mean more impacts. So just something good to be aware of as a designer. Next slide, if I can get it advanced. Okay. So with temporary bridges, there are definitely some limitations. We want to, and this goes back to how we design that detour. So this is going to be our roadway designers. We want it as level as possible. We really want to try to avoid super elevation, if at all possible, because there's limits on what you can do with the bridge as far as tilting it. And then as far as wedging our asphalt, that creates problems as well. So, if you have asphalt on a level deck and you're trying to get super elevation, what you're going to have is you're going to be real thin on one side and you're going to be very thick on the other. And so there's built-in curbs into these deck panels. And so you're going to really start running into problems on the opposite side with your curb height. There is minimal amounts that they can tilt the bridge, and Acro has told us that on a 100-foot single span, they can tilt it 1%. And then if you had a 1% asphalt cross slope, that would be sufficient. But if you start getting outside those realms, it's going to be difficult and outside of what they can do with their bridge. So we need to be thinking about that when we're designing these. And if we can get it in a tangent section without super elevations, that would be great. They do make custom sloping transoms, and I'll have a picture of it in just a second. But that's extra money, and those aren't as available. So it's going to be harder to get those if they're tied up on other projects. So really, if we can be in a normal crown section with a straight bridge, that's really what the goal we need to try to do if we can make those adjustments in the detour alignments. So this next slide just kind of gives you an indication if you had a super elevation, how that's going to be real thin on one side and then the opposite side, especially if you get a really wide bridge where you're eating up your curb on the opposite side, and that can create problems. So here's the picture of the tapered transom. Again, this allows the bridge to be flat while also building in a little super elevation into the bridge. So something that's to be aware of. But again, they're not as available as we would like. Okay, so that's it for temporary bridges. We're going to kind of get into a new topic now, rebar congestion. This is something that as a designer, you need to be thinking about. You know, I'm not a designer, but you know, you go through all your calculations and your dimensions and your amount of steel, and you start detailing it. You need to be thinking about constructability in mind, because when you start getting a lot of reinforcing steel packed tight in together, you are going to potentially be creating problems in the field. First of all, just tying it and understanding where everything goes, but also getting that concrete good and consolidated around all that rebar. And if we don't get the concrete around the reinforcing steel, then it's not doing the job it needs to do. So in this picture here, you can see there's a lot of reinforcing steel, different angles. And then you've also got mechanical couplers in here, which take up space, make it tighter. So I think this was from a pilaster from a maybe a post-tension temporary, I mean a pedestrian bridge. And so you start dealing with these unique designs, you're gonna get additional reinforcing steel, but it's something that you really need to be aware of throughout the whole design process. And I'm just clicking through different photos just to give you some examples of things we've seen where it's really tight rebar spacing that can lead to problems and so forth. So I know there's sometimes a little delay in the slides, but this is a picture of a drilled shaft cage for a railroad project. And railroad projects, they get over designed, and so there's a lot of reinforcing steel in those cages. And you can see here, when you start adding splices to those bars, there is not that much room in between those vertical bars to get that concrete mixed between. And if you can't get that concrete is going to be placed down the center. If it doesn't make its way to the outside of the cage, then we're not going to get the product that we want. And in a drilled shaft, it's very difficult to check and find out if that's actually happened. The inspector has to be constantly dropping a tape in the center of the shaft and the outside of the shaft to compare the two volumes or the two elevations of concrete. So it's something that needs to be done, but it can lead to problems. These two pictures here are of some columns that had similar issues with the tight rebar, where the concrete did not make its way through, and you can see the problems that creates. Now, admittedly, if the contractor did not put the rebar cage with the correct offset from his forms, or the cage shifted, this same problem can occur, and that can lead to severe maintenance issues, especially if we don't catch it and it looks good, and then years down the road, the rebar starts corroding and spalling. This next slide is a detail from a in-bent diaphragm, and you can see on the plans the K1, K2 bars, they look like there's plenty of room in there, but you start looking at splices and so forth. And this next slide kind of is what you kind of get. There's a jumbled up just bundle of bars down at the bottom, and that's not good. So we want to try to avoid that. The next slide here, this is a hammerhead cap that I got a picture of looking down. With a hammerhead cap, it's deeper, so it requires a trimmy to be poured because we don't allow concrete to drop more than 5 feet. So trying to fit a trimmy down this tight spacing is difficult. But then when you take into account the two 13-foot splices, and you've got all these splices at the same location, then you are even tighter. And so that really creates a problem on trying to pour that concrete appropriately. I took 3 different examples of some hammerheads drawings, and just to show you the differences between the two. This first one, which is the one I had the pictures of, 6 inches. So that's pretty doggone tight trying to get that concrete placed through there, especially with the trimmy and splices. The middle slide here, it was a little bit wider cap, so we had a little bit more room, but that was spaced to 8 inches, which was a little bit better. This last one here, you can see they kind of tightened up the spacing a little bit to create these 10.5-inch gaps on either side of the center. So that made it a lot easier to pour. Now the contractor can potentially leave some of these bars loose and move them and shift them and then tie them when they get to the top, but you know, that can be difficult in itself. So be thinking about that as you're designing these things. So there's some of the things you can do: identify the designs with congested rebar, upsize the member if necessary, stagger lap splices. That's probably a key. You know, if you can stagger those lap splices so they're not all at the same location. Think about how the concrete will be vibrated. You know, we get vibrators and things stuck a lot of times. And then, you know, special concrete mixtures. We have allowed recently a change to our specs where we're allowing increased slump up to 6 inches with water reducing admixtures. So that opens up the door for contractors to use different types of mixes. And if necessary, if they get approval, they can go up even higher if we need to. And then so those additives, and then smaller aggregate sizes, keep that in mind. The ACI has guidelines and recommendations on maximum aggregate size based on dimensions and rebar spacing. So make sure you're aware of that, but still, even with those things, it can be a problem. So keep these things in mind as a designer as you're going through it. All right, Cameron, turn it back over to you. Cameron, I think you might be on mute.
How's that?
That's better.
Okay, we did have a question in the chat concerning this about, are the deck geometry factors that we had discussed before on concrete decks applicable to others like cord slabs and box beams? No, not exactly, but we do have some concerns on those as well. One of the things that we can have problems with, all our precast concrete members should have a camber in them. And all of them pretty much are going to have either a concrete or an asphalt overlay on them with a minimum thickness. One of the places we end up with problems on those is if we've got a sag vertical, which a lot of times here in the mountains we have those. So you're combining at the end of this bridge, you've got you're compensating for the camber because you got to have that minimum thickness over the center of the girder, plus this thickness, plus whatever that vertical curve is doing to you. And we can end up with some pretty high barrier walls at the end because you know, your barrier wall is going to be based off of finished grade. So if we've got 8 inches of asphalt at the end of this thing and 2 inches of asphalt here compensate for camber, 8 inches compensating for a steep vertical curve, and we got this 1.5 inches asphalt for the minimum thickness in the middle, that's 11.5 inches of asphalt. Now your 42-inch barrier just went up to 53 inches tall. And if it's like a standard jersey shape, they can't compensate for that in their forms, and it can't be slip formed. It turns into a barrier that's going to have to be hand formed. You know, you're also putting a whole lot of additional weight, which luckily since it's near the barren, it may not be that big of a deal, but additional weight, the thing that, even if we can compensate for this, even if this barrier is going to be one that the contractor had already planned on hand forming, it's also going to change your steel height. And we just got the 5-minute warning. I'm going to try to hurry. It changes your steel height, and you may end up having to have additional steel to compensate for not having the lap splice that you were counting on. So please think about that if you've got especially sag verticals that are pretty steep and you've got an asphalt or a concrete overlay. I'm trying to advance. Next slide. Here's a problem that we used to see, which is not as common anymore. When you've got a cord slab or a box beam, we need to have both bents, or if it's multi-span, all the bents need to fall on the same rate. What happens if you don't? If you've got bents on different slopes, we end up with basically the slabs can teeter. They're not going to bear at all four corners, and we definitely don't want that. So please make sure that all the bents are on the same slope. One more thing on geometries, and this applies not only to cord slabs and box beams and concrete decks, all. if you've got a skew and a phased bridge, we need to pay attention to this area over here to make sure that we've got enough substructure to take care of our superstructure. One of the things that I have seen in the past is we've got enough cap here to set a girder on way out here. And if we can set a girder on that thing, we can have deck even further out than that girder. The problem arises back here. If we have a deck that is designed like this and we've got barrier over here, and in the next phase we're supposed to have traffic running over here with a barrier on the edge of this phase, we might not have enough back wall to build our approach slab. We've only got enough back wall in this example to build approach slab out to here. You know, this may be able to be compensated for if we just don't have room out there to do this. Maybe we need to skew the substructure. I know normally we want it on a, cut off at a 90, but we may need to skew the substructure in order to have this out here. But what ends up happening is we can get this much room in on this design. This is where we could put the barrier, because that's as much approach slab as we've got. And we can't make an overhang out here to pour that approach slab. This is where we wanted originally, then we've got troubles. We don't have enough room to shift our traffic around. So if you end up with a situation with on a skew and it's phased and it's tight, please pay special attention to that and give one of us a call if you got any questions about that. All right.
So at this point, I think we're probably approaching the end of our presentation, and we ordered these in order of importance. So if we want to allow this time for Q&A, I would probably stop here and open it up to questions.
Aaron and Cameron, I just want to thank you for a great job. I mean, that was extremely informative. We got a lot of great feedback about it. I saw that Cameron had answered some of the questions in the Q&A. If there are any questions, Cameron or Aaron, that you feel that the group would benefit from hearing from, please let me know, and we can go over those very quickly.
Just quickly, we got one question about dropping the aggregate size to compensate for congestion. Yes, we have done that in the past. One of the examples that we had in the pictures, that was one of the recommendations I made, was to drop down to a smaller aggregate size. Aaron, jump in here if you see anything you want to answer.
Yeah, somebody said, does removal of temporary bent after the deck is poured result in further deck deflection? Temporary bents are used for the erection of the girders, but after everything is erected, those temporary bents should be pulled down before the deck is poured.
Well, we've got one right now where that's not happening. The deck is cast. Okay. The deck gets cast before the temporary bents are removed, and I would, if it was me, I would treat that as a permanent bent if I was thinking about pour sequences, and because what we're looking for there is to eliminate any places where we've got negative moments in the top of the slab. So I'd just treat it as a permanent one.
Yeah, and there may be a little bit of deflection, but since it's all composite, it's probably not going to deflect much more after you pull that down.
Yeah.
Great. Thank you very much again, Aaron and Cameron. That was a phenomenal presentation. I know a lot of us, or all of us, have learned a lot from that. I want to thank you for your time. If you can stay tuned for a quick message from our team, this concludes our structures constructability segment.